Hey everybody, Ms. Butler here with a video about titrations. And actually this is kind of part one. We're going to do strong acid, strong base titrations. Okay, so for these notes and for learning titrations, it's kind of helpful to think about what the particles are actually doing. So we're going to be drawing some particle pictures or particle representations in our notes. And so I just have some rules for you when we're drawing particle pictures. The first thing, particles must be countable. And I'm a pretty lazy person. I don't really want to count more than 10 to 15 particles in one picture. So something like this, not countable. Like, is that line 1 particle? Is it 5 particles? Right? I don't want to count that. You don't want to count that. So we want to make sure the particles are easy to see and they're countable. We have to follow the law of conservation of matter, which says that matter cannot be created or destroyed. So if I start with a certain amount of particles before the reaction, then the number of particles after have to be the same. You need a key that tells us what particle is what. States of matter is represented by the spacing between the particles. So if you have a solid, you'll show those particles close together, a liquid a little more spaced out, and a gas even more spaced out, if that's important for your drawing, like if something's turning into a gas or you're creating bubbles. And then for acid-base, ionic compounds are going to break apart. If they're going to break apart, I should say, you should show the correct number of particles. So for example, instead of drawing one circle to represent HCl, I should really have a shape for the H plus and a shape for the Cl, and then they're bonded together. So 2 particles or 2 shapes touching represents being bonded, and then they can break apart into the ions. What I tell kids is that if there's one you'll do one different shape for each capital letter, and then you'll have them touching to show their bonding, so that way they're able to break apart. One thing that we can get away with, polyatomic ions, so something like nitrate, NO3 with a -1 charge, you can do one shape for that because in most of our drawings, that nitrate is not going to break apart. So for example, if I have something like KNO3, I can draw maybe a smiley face particle for my K and a triangle particle for the NO3. And that will still work because we can break it apart into K plus and NO3 minus. All right, you should have 2 things, well maybe 3 things for this set of notes. The first one, and mine's already kind of filled out, is a drawing that looks like this. This is where you're gonna actually take the bulk of your notes because we'll be drawing particle pictures and writing notes about the calculations next to each drawing. And then you should also have a set of slides that starts with those particle picture rules. I think yours is 6 on a page, I can't really remember, but it's just 1 page. So it's mostly gonna be this guy that we're taking notes on, but then we'll do some practice problems on this slides. Additionally, you might want to have a few colors because the particle drawings, it's easier to draw with different colors. So if you have different colors, pens, pencils, things like that. I used 2 or 3 colors, definitely 2 for sure, the red and the blue, but if you want your notes or your calculations to be in a different color, I might recommend a 3rd. All right, here we go. There's kind of a lot going on this diagram that we're going to be using, so I just want to point some things out. First of all, they give us an equation, HCl, which is a strong acid. It's on our list of strong acids to memorize. NaOH, which is a strong base. And those guys are going to be reacting to make H2O and NaCl, right? Pull out the water, NaCl. So when we have strong acids and strong bases, we know those are going to break apart completely. So I suggest you write the net ionic equation somewhere on the top of your page. So when we have a strong acid, strong base titration, the net ionic equation is always going to be H plus OH minus makes H2O. So we're going to start at the beginning, and as you can see, this graph is measuring the pH, so that's the negative log of H plus, versus the volume added. So in this particular example, we're going to start with just HCl in our beaker, and over time we're going to slowly add NaOH. So as I keep adding milliliters of NaOH, I can see that my graph is going to start to slowly increase. We're going to get a spike, and then it's going to level off again. And that's the pH that I'm looking at. We slowly go up, we spike, and then we level off as we add the OH. Okay, I also have a key, so we're going to draw a lot of particle pictures. My H plus is going to be a red circle, my hydroxide is going to be blue and red, and then water is going to look like Mickey Mouse, 2 reds for the 2 hydrogens and 1 blue circle for the oxygen. So put that key, put that balanced equation, and then we're going to get started. All right, so we are going to start with this green dot right here at the very beginning where 0 milliliters of the OH has been added. So this is, remember, volume of hydroxide that's added. This is the pH. So this picture that I want you to draw represents before the titration, before we've actually done anything. So I'm going to start, let's just say, with 10 HCl particles dissolved in water. So this is now an aqueous solution, and because it's a strong acid, all of those H's are going to pop right off. So I'm going to ignore the chlorine. That will make my picture just too crowded. So I have 10, as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H plus ions in my beaker. This is at the very beginning. Because H plus is a strong acid, we know it breaks apart completely. That's why I have exactly 10 H plus particles. That means I have no water and no hydroxide because we haven't actually added any hydroxide, so they haven't reacted to form any H2O yet. So if this is the beginning, we haven't added anything, how do I find the pH? Because that's what we're measuring on this side of the graph. Well, the pH is going to be determined by the concentration of H plus by the strong acid. So this is just like objective 1, where we're going to take the negative log of H plus, and that will give us the pH. And we're allowed to do that because HCl is a strong acid. So if I have 10 molar HCl, I have 10 molar H plus. Negative log of H plus will give me the pH. So take a second, sketch the picture, and then what I did is right below that beaker, I wrote before titration and what's here in blue, so that I know if we're before the titration starts, I know how to calculate the pH at that point in time. So I've now started to add a little bit of hydroxide. So I have a bunch of H plus. As soon as I add a little bit of OH, acid, base, boom, those guys are going to react together to make water. So there's no stopping an acid and a base from reacting to make water. So I add a little bit of hydroxide, all of that's going to react with some of the acid that's there to make some water. So let's add a little more. Really, at any point from when you start until we get to a special point that we'll get to in a second, we're going to do this same process. So I'm not going to show you like every little step of the way. Let's just say we stopped right here. And let's pretend that we're doing this titration and we have added 4 moles of hydroxide. So I had my 10 moles of H plus, and now I've added 4 of hydroxide. Well, we know that it's a 1-to-1 ratio. So if I add 4 hydroxide, that's going to make 4 water molecules. So that would leave me with 6 H plus left over, and we will have no hydroxide left over. So this is like excess. This is like remaining. And produced. Okay, so we've added some hydroxide. It's reacted to form some water. I still have extra hydroxide, and then now we've made some water. How do I figure out the pH? Well, the pH is going to be determined by how much excess H plus is in the solution. So we've done the reaction, now how much is left in excess. So to solve, we're going to do a little stoichiometry. We're going to figure out how many moles of excess H plus exists, which we got right here. We can figure out the molarity by taking the excess moles divided by the total volume. So the volume that we started with and the volume of hydroxide added, and then the negative log of that concentration will give us the pH. So in your picture, I want you to draw these particles and label how much is there, and then you'll fill out what's right here below that beaker number 2, some OH added, and then how to find the pH. So we're going to just keep on going, keep adding hydroxide, right? So we keep having a little bit of excess H plus. So we're going to find the pH the exact same way we did on that last slide. All right, keep going. We're adding hydroxide. So now let's say we had 8 moles of hydroxide. So that means I started with 10 of H plus. I added 8 of this. So we're going to make 8 water molecules, and I'll have 2 of the H's left over. So how much hydroxide will be in my beaker? None, because we used all 8 moles, so there's none remaining. I have 2 moles excess, and I have 8 moles of H2O produced. So that's my BCA table, but I'm using the particle picture to kind of decide my BCA table, right, based off how many are left. So in this situation, we're going to determine the pH the exact same way. It's based off how much excess H plus there is. So this is your beaker 3. We are going to do stoich. We're going to figure out how many moles of H plus are excess. We're going to divide that excess moles by the total volume, so the starting volume of H plus and the volume of the base that we've added, and then we'll take the negative log of that concentration to find the pH. All right, you should be approaching beaker 4, and there's a very special point. So if you notice, this graph shoots right up. And think about your indicator when we just did our very first titration. It went from maybe being light pink to hot pink very, very fast, because as you can see, this range of pH really goes down from like 3 all the way up to 10 very, very quickly with a small amount of volume added. So the midpoint of this straight line, so the midpoint of this line segment that shoots right up is very special. Let's talk about it. The midpoint of that graph is called the equivalence point, or sometimes you'll see it called as the stoichiometric point. This is when enough hydroxide has been added to react exactly with how much H+ is there. So they both react completely. In the strong acid, strong base titration, at the equivalence point, the only things present are Na+ from the sodium hydroxide, Cl- from the H+, and water. Well, Na comes from NaOH, which is a strong base. And so if you're the conjugate acid, like Na+, from a strong base, you're not going to have any acidic or basic properties because I came from a strong base. If this were a weak base, then whatever was the conjugate would have some acidic properties. But when you are the conjugate acid from a strong base, you have no acidic or basic properties. Same with Cl-. HCl is a strong acid, so Cl- is its conjugate base. And because this is a strong acid, there are no acidic or basic properties from Cl-. So that means the only thing really that we care about floating around is the water. So we have water, and water has a pH of 7. So because water at room temperature has a pH of 7, the equivalence point for a strong acid, strong base titration will have a pH of 7. So we've added now 10 moles of hydroxide. We started with 10 here, we added 10 here, so they're both going to react completely to produce 10 molecules of water. That means I have no excess of H+ and no excess of hydroxide. They perfectly react. And because this is the equivalence point and it's a strong acid, strong base titration, we know the pH is gonna be 7. And you can see, here's pH 7, it lines almost right up, but this is what happens when I do things on the smartboard, okay? So when I start these problems, whether a graph is provided or it's just a calculation-based problem, I like to sketch a picture. So I have a strong acid, strong base titration. Here's what this means. Down below, in my flask, I have the strong acid. Up in the burette, I have the strong base. So I'm adding the strong base. That's like this graph we've seen here. So we start at a low pH because there's only a strong acid in the flask. And as I add the hydroxide, my pH is going to climb. It's going to shoot up. My equivalence point is at 7. And then we'll eventually level off to, which we'll get to in a second. I can also do the opposite. I could have a strong base down low and add to it a strong acid. In that case, my graph is going to be like a mirror image. I'm going to start at a high pH, we're going to slowly go down, we'll shoot down, and then we'll level off. The equivalence point will still be at 7, but you can see the graphs are like mirror images of each other, depending if we have a strong base or a strong base that we're adding to a strong acid, or a strong acid we're adding to a strong base. So you'll see both of these problems. I'm just talking through this one in detail, but you solve everything the same way if you're starting with the base. The only difference is you will be finding the pOH, which then we can say 14 minus the pOH to give us the pH, right? So if I can find the molarity of this, once we've added some strong acid, how much is excess, right? Excess concentration of strong base, negative log of that is pOH, and then 14 minus the pOH would give me this high pH value. So now we've passed the equivalence point, so what we should see is excess hydroxide because we've used up all the H+, so we're adding now excess hydroxide in our lab. This is where it starts to get really bright pink if we're using phenolphthalein as an indicator. So now even more hydroxide, we don't have any more H+. Still going, lots of hydroxide being added. You can see my graph is starting to level off pH-wise. So let's stop here. Let's say I've now added a total overall of 14 moles of hydroxide. Remember, I started with 10 moles of H+. So if I have 10 moles of H+ and 14 hydroxide, now my H+ is my limiting reactant. I can still only make 10 moles of water. So I still only have 10 moles of water produced. I've used up all the H+. And that means because I've used 10 of the 14 moles of hydroxide, there's 4 moles remaining, or excess. So how do I find the pH? Well, the pH is going to now be determined by the excess hydroxide. So I'm going to do stoichiometry to find how many excess moles. In this case, it's 4. I'm going to divide that by the total volume, so H plus and hydroxide added. And then now I have my concentration of OH, so I can find the POH, which is the negative log of OH. And then to find pH from that, I'll take 14 minus the POH. So this is just like my pH square. Once I have concentration of hydroxide, we're just doing whatever direction you prefer to get to pH. So in your diagram, this should be number 5, and you can fill out this drawing and then these guys below the beaker. All right, so in this problem, I have 200 mils of 2 molar NaOH added to 500 mils of 1 molar HCl. What is the pH? So first, I'm best if I have a picture. So I know that it says NaOH is added, so that means it's coming from the burette, and NaOH is a strong base, so I'm just going to say it's hydroxide. And down below, this must be my acid, and HCl is a strong acid, so that is H+. So my first step is to find the moles of OH minus and the moles of H plus. So I have 2.0 molar NaOH, which is the same as 2.0 molar OH minus because it's a 1-to-1. One molecule has 1 hydroxide. I want to know the moles, and it's 200 mils, which is 0.2 liters. So if I cross multiply these, put this over 1, crisscross, crisscross, that gives me X is going to be equal to 0.40 moles of hydroxide. So that means I'm adding 0.40 moles. Down below, I have 1 molar HCl, which is the same as 1 molar H+. There's 1 hydrogen and it breaks apart completely. I want to find moles, and it's 500 mils, so 0.5 liters. Toss that guy over 1. Let's crisscross. That will give me X is going to be equal to 0.5 moles of H+. So this is 0.5 moles down here. Okay, so that's our first step. Find how many moles of each. Step 2 is the stoich to see what is limiting. So this is a strong acid, strong base titration. So my equation is always H plus OH minus makes water. We do before, change, and after, and BCA is only moles. Don't get it confused with your ice tables. This is just moles. And so I found that I have 0.4 moles before they actually react, and I have 0.5 moles, which means I'll have no water to start. 1-to-1, so minus X. This is plus X, and so now we can find X. For my H+, we're going to take 0.5 divided by the coefficient 1, so that's 0.5. For my OH minus, we're going to take 0.4 divided by its coefficient 1, so it's 0.4. The smaller one is your X, so this is my X, which means my hydroxide is the superstar. It's going to run out. So now we can just fill out our table. Minus 0.4, minus 0.4, plus 0.4. So we take B plus C, so 0.5 minus 0.4. Oh, sorry about that. That'll be 0.1 moles. 0.4 minus 0.4 is 0 moles. And 0 plus 0.4 is 0.4 moles. And now we can see that we are, if you picture your titration graph, let's do that over here. We have the volume OH added. We have the pH. We know we start low. Let's try that again. Start low, shoot up like this. So at this point, I have excess of the H+, and that's what we started with. So realistically, we are in this range right here. We're not quite at the equivalence point. Oops, I want my pen. We're not quite at the equivalence. and we're past the beginning, so we're in this range right here. So if you look at your particle drawings where we talked about calculation, in beaker, really we're at like beaker 2 and 3, which told us that the pH is determined by excess H+. So we're going to take my excess H+ and find concentration. So I'll take my 0.10 moles, and we're going to divide it by the total volume. So first, I started with 500 mils, so 0.500 liters of H+, and I added 200 mils of the base, so added to 0.2. When I solve out for my molarity, I get 0.14 molar. Very last step, that is concentration of H+, and we know that the pH is equal to the negative log of H+. So I'm going to take the pH is equal to the negative log of 0.14, and my pH at this point in the titration is 0.85. Okay, a couple of things for the AP exam. You have to show this right here. You can't just go from 0.4 molar to pH of 0.85. I know it's a very simple equation to plug into your calculator, but the AP exam wants to see that you know how to go from the concentration of H+ to the pH, so show this equation and your work right here. Okay, so there's your first sample problem. Here is that problem one more time. I wrote it ahead of time just so it's a little bit neater, but yep, same exact thing we just did. All right, I would like you to pause the video and try this one. I have a couple suggestions. Make your little sketch and tell me who's in the burette, who's in the flask. And after you do your stoichiometry, it's kind of helpful to mark where you think you are on the graph, because that will help you decide how the pH is determined. Are you past the equivalence, at the equivalence, before the equivalence? That will tell you where you are on the graph, what equations you need to do to find your pH. So pause the video, and I'm going to put the answer up in 3, 2, 1. All right, so hopefully you tried this one. I am adding the hydroxide to the H+. So first step, find moles of each. So I just took my molarity as moles divided by liters, so I found moles of each. The stoich is 1:1, but it's good to see it in the BCA table. So I have my starting amounts. My hydroxide is going to limit because I have less of that, so X must be 0.0048. And so then I can do B plus C, so 0.005 minus 0.0048 gives me 0.0002. And then we do the same thing for the other guys. So in this case, because I have excess H+, the pH is determined by that amount of H+. So we're still in that same region we were last problem. So I take the moles excess, divide it by the total volume, the hydroxide that was added, and the starting H+. And I can find my concentration of H+. pH is the negative log of H+, so I just plug that in, and I get my pH 2.69. All right, you practice this one, 25 mils of HCl, and then we're adding some strong base to it. So you should be able to draw your sketch, figure out where you are on the titration curve, and solve for your pH. I'll put the answer up in 3, 2, 1. All right, hopefully we were able to, at the very least, start this problem. So I drew my little sketch. I have 0.1 molar of this strong acid, HCl, and then 0.1 molar of a strong base. They didn't tell me what it was, but that doesn't matter because we know strong bases break apart completely. So if I have 0.1 molar of the strong base, I have 0.1 molar of OH, and so I can find the volume that was added, turn it into liters. That allows me to find moles of OH, the volume of the HCl in the flask times the molarity. That will give me the moles. It's a 1:1 stoich, so H+ limits, but let me just show that because we should always show our BCA table. H+ plus OH minus makes H2O because it's a strong acid, strong base. I plug in my before moles, minus X, no water to start, we're adding X. So if I take 0.0025 divided by 1, 0.00375 divided by 1, that makes my smallest answer, the 0.0025, so that is my X, H+ limits. So there's no excess when I plug in this, so 0.0025 minus X gives me 0, 0.00375 gives me 0.00125, 0 plus that gives me 0.0025. So there's excess OH. So we are past the equivalence point, which means the pH is determined by the excess amount of OH. So let's figure out the concentration of OH. I take the moles excess and divide it by the total volume. That's the volume of the acid and the volume of the base that we've added. That gives me 0.02 molar. I know the POH is the negative log of OH, so I can solve for POH. Notice I showed all my work. And then a quick little subtraction, 14 minus the POH. So 14 minus that 1.70 will give me the pH, 12.3. All right, at this point, you should be able to do objective number 4, which is the titration and indicator problem set. You should be able to do objective number 4, question 64. You should be able to do the entire thing. I do believe this question is worth 5 points because there's 5 separate steps. You're basically calculating the pH at 5 different times or points on the titration. So what I've done is I picked 64D. So we have this strong base and a strong acid. You should be able to do the entire problem though. So my thinking is, if you stop the video here, try the problem up to D, and then you can check your answer here to make sure you're on the right track with letter D, and then you can finish up the rest of the problem. There's not much else on the problem set for problem set 4 that you can do yet, but again, this is a long time consuming problem, so you might as well get it done so it's fresh on your brain because of the video. I'll put the answer up to 64D from objective number 4 in 3, 2, 1. All right, so hopefully for this, you got that we are at the equivalence point. The reason we know we are at the equivalence point, because the moles, when I solve for moles of each, the moles of OH and the moles of H plus are equal to each other. So for strong acids and strong bases, when moles equals moles, we are at the equivalence point, which means even though this is a backwards titration curve where we start with the base and we're adding the acid, it means that the pH is 7. So the pH is always 7 for a strong acid, strong base equivalence point. What this helps you with for the rest of the problem is you know that letter D was the equivalence point. So that means A, B, and C must be before the equivalence point. So you're going to be using those calculations before the equivalence, and letter E must be after the equivalence point. So that should hopefully give you a frame of reference to help you with the rest of this problem. Good job, everybody.